Hi, I'm Mario and I'm going to present the joint work by a robot and myself, universal test time adaptation through weight ensembling, diversity weighting and prior correction. So the goal of test time adaptation is that in cases where we have a deployed model and this model is subjected to changes in distribution, that we use the current test data to adapt to these distributions. Since we don't know the nature of the possible distributions or the scenarios beforehand, a method proposed for test time adaptation has to work for all kinds of environmental conditions, which we denote as universal test time adaptation. Recent methods show that they fail in certain settings or distribution shifts. Coming next to our proposed methodology, we will start with an overview and then dive into our components. Finally, we give a limited overview of our experiments, showing results for the continual and correlated setting, and finally drawing a conclusion. So, the overall method is based on self-training. We have a soft likelihood ratio loss combined with a symmetric cross entropy loss, which forces to learn some invariance to small changes in our input space, and weight these with diversity and certainty weights. To maintain generalization, we employ weight ensembling and finally apply prior correction to our output. So going into certainty and diversity weighting, entropy minimization can result in models becoming biased or worse, collapsing to a trivial solution. Therefore, we propose certain and diverse predictions by calculating the weights shown here. So we have diversity weights, which are 1 minus or the cosine similarity between our current predictions and an exponential moving average of our recent predictions. So in case some classes might be underrepresented for a certain amount of time, if they reappear, they receive a higher weight. Furthermore, we apply certainty weights in the form of negative entropy to give more reliable certain predictions a higher weight. Coming to weight ensembling, if you think about if we adapt our model to a narrow distribution, so our current domain shift, this will likely lead to a loss of generalization. And this then might hinder further adaptation to other domain shifts. To maintain this generalization and prevent forgetting, we leverage our initial source model, which was originally trained on a broad distribution and shows good generalization capabilities, and continuously introduce the source weights into our current model weights. We also showed that this actually has this effect as mentioned. So here, first of all, considering TENT entropy minimization without weight ensembling, we can see that if we adapt a domain here on the left and evaluate it on other domains here from ImageNet C, then we can clearly see that, of course, the performance improves here in terms of reducing the error rate, but for all other domains, the error increases, namely we have loss of generalization. Now, using our weight ensembling on top of 10, we can see we can still adapt to the distribution shift and also remain much better the performance on other distribution shifts. Now, coming to our third component, prior correction, let's first imagine a scenario where no domain shifts exists and only the class distributions between the training and test data differs. A non-adapted model then will underperform because our learned posterior will deviate from the actual posterior in terms of our shift in prior. So we can recover this performance loss by correcting the deviation posterior according to this equation, namely using the ratio between our actual prior and the learned prior. Since we employ diversity weighting, we assume a uniform learned prior, and now the question still remains, how can we estimate this true prior? The difficulty arises since we only have a batch of data available, so we employ a additive smoothing scheme with an adaptive gamma here, and this gamma will be small if our batch of data tends to have a prior or high priors for few classes, and is large if our batch tends to be uniform. Coming to our experiments, so first looking at the continual setting, so we have uniform class distributions and encounter, if we have multiple shifts, we encounter them sequentially. We can already see that for many recent methods, performance can be worse than the source baseline. This is the case for TENT, SAR, COTA, RMT, and LAME. Our method shows a strong adaptation, actually best or state-of-the-art results on all these benchmarks and also for different architectures. Now, having also a look into the correlated setting, we can see here on the left that here the source baseline, the dashed line in blue, only LAME and ROID outperform the source baseline. All other methods for at least some of the benchmarks show worse results. Also here on the right we show the influence of prior correction, here in orange, and ROID including prior correction in green, and can see that for increasing correlation we can benefit from prior correction for a reduced or resulting in a reduced error rate. And then finally, drawing a conclusion, we showed that current methods, even proposed for challenging settings, often fail to fully address the whole picture of universal test time adaptation. Our proposed method significantly outperforms existing approaches in the challenging setting of universal test time adaptation. And also through our analysis, we provided valuable insights into the challenges that arise when models are subjected to self-training during test time. If you want to dive into more details, please have a look at our paper.